Okay, so let's state some fundamental theorem about ordinary differential equations, such as the Cauchy theorem for the existence and uniqueness to a given Cauchy problem, and other results concerning the flux of a given function, regular function, and also some properties of integrable fields. So let's start with the following definition. Let W be an open set of Rm. Let J be an open interval of the reals containing the 0. Let F from W times J into Rm being k regular functions in all the variables. And let J delta equal to minus delta delta be a subset of J containing obviously the 0. Then we say that a function y from J delta into W satisfies the Cauchy problem for f with initial point y0 equal y of 0 if and only if y prime L of t is equal to fl x1t xmt for each t belonging to J delta. In case in which f satisfies the Lipschitz condition, there exists a constant c such that for each zeta and w belonging to capital W and for each t belonging to J, the norm of the Euclidean norm of f zeta t minus f w t is less or equal to c times the norm of x minus zeta, or zeta minus w, or w minus zeta is irrelevant order. Now, assume that f is a k regular function from wj into Rm satisfying the Lipschitz condition. Then there exists a delta greater than 0 and a unique function y from J delta into W such that y satisfies the Cauchy problem for f for each initial data y0 belonging to W. Furthermore, the function y is k plus 1 regular in the t variable. We have this kind of thing. Now let W be an open set of Rm. We say that U is relatively compact in W if and only if the closure of U is compact in W. This is holds for every topological space. A theorem holds. It's the theorem about the flux of the function f, and it's the following. Let f be a function, a k regular function satisfying the Lipschitz condition, f from W times J into Rm. So let as I was saying, let f from W times J into Rm be a k regular function satisfying the Lipschitz condition. Then there exists an open interval J delta minus delta delta contained in J, and a function g from a relatively open subset U of W, and a function g from U times J delta into W such that g of y0 is equal to y, and g of yt is equal yt, and yt satisfies the Cauchy problem for f for for the initial point y equal g of y0. The function g is called the flux of f, and furthermore it is k regular in the first time variables and k plus 1 regular in the t variable, in the time variable. Now, in the case f is not explicitly dependent on the time, so it's a function from w into rm, the function g, the flux of f, satisfies the so-called semi-group property. That is, if f is a function from w into rm satisfying the Lipschitz condition, and let g be the flux of f, then assume S1, S2 and S1 plus S2 belonging to J delta, and pick up an X belonging to U, and assume Gx S1 belongs to U itself. Then G of S1 plus S2 X is equal to G of G S1X S1. This is the property of semigroup. Now, given a vector field, we say that a curve gamma from J into M, where M is a differentiable manifold, we say that gamma is an integral curve of x if the derivative of gamma with respect to t equal x of gamma t for each t belonging to J. This is the definition of integral curve for a given vector field. In coordinates, we have that the curve gamma is mapped into a curve phi of gamma t equal to x1 t xmt, and the field x is mapped into another field d phi of x equal to the sum over I of ai x1 xm partial derivative with respect to xi. And we say that phi of gamma t is an integral curve of d phi of x if and only if the derivative with respect to t of xi are equal to ai x1 t xmt. This is the definition. There's another object which are called variable vector fields. A variable vector field of class k minus 1 is actually a map from m times j into m, which is k minus 1 regular, and for each t x of point t, a variable vector field is a map x from m times j into tm, and such that for each t in j, x of capital X of xt is a vector field of M. An integral curve for a variable vector field is a gamma from J into M, such that the derivative of gamma with respect to t is equal to x, capital X, of gamma t. This is the definition of k minus 1 regular vector field. There's a theorem which is the following. Let M be a k regular or a k class k differentiable manifold, and assume that X is from m times j into Tm, a variable vector field. Then there exists a neighborhood W contained in m times j, which is a neighborhood of m times 0, and an unique function g, and the function g from W into m, such that for each x bar belonging to m, g of x bar t equal gamma t is an integral curve of the variable vector field x, and gamma 0 is equal to x bar. Furthermore, if we pick up a point P belonging to M, then assume that P t bar belongs to W, then the function g of Pt equal ft is of class ck in a neighborhood of the point t bar, where we have assumed that the variable vector field is of class k minus 1, if I haven't said that. We have this kind of theorem. So let m be a k-regular function, let x be a variable vector field j times m into Tm, a variable vector field of class k minus 1, then there exists a neighborhood W of m times j, a neighborhood of m times 0, such that for each x belonging to m, g of x bar t equal gamma t is an integral curve of x, and gamma of 0 is equal to x bar. Furthermore, if we pick up a point P belonging to M and assume that Pt bar belongs to W, then the function f of t equal g of xt is of class ck in a neighborhood of t bar. This was the theorem. Okay, another theorem is the following. Assume that, and is the prolongability of integral curves. Assume that gamma is an integral curve of x, a vector field over m, and gamma goes from interval AB, let's call it j, so it's a curve, so goes from j into m. Then there exists another interval j bar which contains j, and a curve gamma bar which goes from j bar into m, such that gamma bar is an integral curve of the vector field x, and the restriction of gamma bar to j is equal to gamma. This is the theorem on the prolongability of curves. But we must say, so let's repeat this theorem because there was something missing. Assume that x is a vector field over m, assume that gamma from j into m is an integral curve of m. In case in which gamma of j is relatively compact in M, then there exists an interval j bar containing j, and a curve gamma bar from j bar into M, which is an integral curve of x, and the restriction of j bar to j is actually equal to gamma itself. So we must include that the image of j, the image of j via the curve gamma is relatively compact inside M. Now we are going to talk about a little bit about the integral submanifolds of a given differentiable manifold. And in particular, we are going to give a necessary and sufficient condition in order for a manifold to have an integral submanifold. But what are those concepts? Now we are going to explain. Let x1, xk be a set of vector fields over M, smooth vector fields over M. And set dp equal x1p, set dp the subspace of tpm, which is generated by the vectors x1p, xmp, xkp. So dp is a subspace of tpm. Now we say that n is an integral manifold of the set D of k vector fields if and only if tpn is equal dp for each p belonging to n. Now we say that n is an integral manifold if this is an integral manifold of D if this holds, and we say that D is integrable if this holds. Now we are going to give a necessary and sufficient condition called Frobenius theorem for the existence of integral manifold or integrability of a set of vector fields. More specifically, we can say that a set D of vector field x1, xn is a distribution or Frobenius distribution just in case dp, just in case x1 p, xk, p are linearly independent for each p belonging to M. This is the definition. Now we say that a Frobenius distribution D is actually involutive if the Lie brackets of two fields belongs to the distribution itself. So if the commutator of two fields of distribution belongs to the distribution, it's involutive. We say that that D, the distribution D, is locally integrable or is a foliation in case for each p belonging to M we have that there exists an open neighborhood W of P such that dW is integrable. So there exists an integral manifold F of dW which passes through P. In this case, we are calling the integrable manifolds F as leaves of the foliation. The Frobenius theorem can be stated as follows. Assume D is a Frobenius distribution of a given manifold M. Now D is integrable if and only if the distribution is involutive. Frobenius theorem. Now let's talk a little bit about linear connections. They are very important because we cannot define the linearity of differential equations on a manifold, and because actually we cannot define easily what is a derivation, the derivative of a vector field. The object which makes possible to define the derivative in some sense of a vector field is actually the linear connection. But first of all, what is a derivation of a vector field? Assume that Kp of M is the set of smooth vector fields defined in a neighborhood of a point P of the manifold M. Then a derivation is a map from Tpm times Kmp into Tpm, which is linear in both arguments and satisfies the Leibniz rule with respect to the second argument. a linear connection is a derivation of a vector field which is regular. In what sense? Now it's a map which satisfies these four properties. Delta f x plus g w of y is equal to f delta x of y plus g delta x of delta w of y. Delta x of y plus zeta is equal to delta x of y plus delta x of zeta. Delta x of fy is equal to f delta x of y plus xfy, and if x and y are smooth vector fields, then delta of xy is also a smooth vector field. Those are the properties. So the map delta is actually can be viewed as a map from km times km into km, even though with respect to the first variable only the local only the punctual value of the field is important. An example can be this: let A be a subset of Rn, and we can define obviously the derivative, the linear connection defined over two partial derivatives, di and dj. This gives the Christoffel symbols, which are a set of m-cube symbols, and if these are given, we can extend by linearity the connection and define the connection for each possible vector field. So we obtain this kind of thing. If we know the Christoffel symbol, then it's easily given the connection. So when we are in local coordinates, the Christoffel symbols provide what is the connection, and if the Christoffel symbols are 0, we obtain the standard connection over Rm. So let A be a subset of M, and x1, xm be a set of vector fields defining the tangent bundle to the manifold M. And obviously we can build delta of xi xj equal to bijk xk, and if the structure constants bijk are known, we can extend the linear connection to the whole set of vector fields, so we can define by linearity these vector fields.